Okay, we are down to the last two videos now into the last chapter of the textbook. One of the things that I found is that students who otherwise are heading straight towards an A will oftentimes, I think maybe because of time crunch, run into some difficulty with this last chapter. And on the final, I get a lot of blank sections on this. It's not difficult material, and you actually have a cheat sheet when you take the test for it. But sometimes there's a difficulty in understanding generally what we're trying to accomplish with this. And if you give yourself some time, work some problems out like they are in the book, I think you'll master this and get the last little bit of material taken care of out of the textbook. The last chapter, Chapter 8, The Way of the Raccoon, is looking at something called logical implications and logical equivalences. You've got a cheat sheet here which is found throughout the chapters of the book with the logical implications and the logical equivalences. It is duplicated at the beginning, and then you get bits and pieces as it moves through 12 different rules that will allow you to manipulate information that you come across. What we're doing here is, unlike Chapter 7, we're not going to be testing for validity. We're going to be doing arguments that are valid. And instead of trying to build a truth table, we're going to take rules, those rules on the sheet, those rules which you'll be given a cheat sheet for, this very sheet when you take the test, and we're going to be able to work through the problems with the rules in front of us. That is to say, you will work the problems out with the rules in front of you. There are 12 rules, and in fact, I'm not even going to get to the 11th and 12th of them because while they are in the book, those are not being used on the final exam, so you don't have to know the last two. We're just going to worry about the first 10 rules. If for some reason you want to learn 11 and 12, they are on the sheets, and you're welcome to make use of them. Occasionally, I've seen students get creative and employ them. As long as you use them right, that's fine, but basically, let's worry about those first 10 rules. The first part of this are the logical implications. And I'm going to explain what we're doing by pointing out rule number 5 just as a way to get started, just as a way to illustrate what's going on. Rule 5 is called simplification, and you're going to learn it as SIM. And simplification is a name for a logical operation. Your premise for the logical operation is a conjunction, P and Q. Your conclusion is one side of that. Now think about what this is saying. If I know that P and Q are both true, does it not follow logically that P by itself has to be true? It shouldn't be that exotic a statement to say that P by itself has to be true. For the same reason, if I know that both P and Q are true, then I should also be able to know that Q by itself is true. You almost want to be daring here and say this is just common sense, or perhaps a name for the screamingly obvious. That is the kind of steps that we have to work with. That's one of the more obvious ones that are going to define what we do in this last section. So let me just show you how these problems might work. You're going to be given certain very basic information, and I'll just give you a simple one. You've given two premises, and all of these will have to be numbered now. I accidentally did that one time on the last video, and it looked a little out of place. So this is how your problems are going to be set up, and this is one of the simplest ones I can give you. You're going to be given a set of premises, and over to the side, usually the word therefore will be here. When I draw it on the board, I just make a little box for it, is the conclusion you're trying to reach. And here's what I'm telling you. Here's a premise and here's a premise. If you manipulate these premises, you can prove this conclusion. So what are the premises? The premises look like this. Premise 1, P implies Q. That is, if P is true, then Q is also true. And I also tell you that P is true. Okay, if P is true, then Q is true, and P is also true. Sounds like Q's got to be true if I just kind of say that out loud. Well, I can deduce that how? What I say when I do this is that there is a rule. It's rule number 1, modus ponens, and I'm just going to put MP here for now, that I can use on lines 1 and 2. And if I use rule modus ponens on lines 1 and 2, I can prove this next step, which is Q. Since Q is the conclusion I'm trying to reach, I'm done. That's the whole thing. That's a simple version of it, obviously. But this is what you're going to be doing on the test. You're going to see this, and you're going to see this, and you're going to be providing this. Logical steps, usually more than one, logical steps that will reach the conclusion I've told you to reach. And you know kind of from the get-go that these are going to be valid because I tell you they're valid. I'm going to explain to you 4 of the logical implications, the first 4 rules, and then we'll work some problems with them. The first one is the one that we just looked at. This is called MP, or modus ponens. And it's very important that I did not do an and there. I have to do this with an arrow. I have to have an arrow, and I have to know that the left-hand side of the arrow, that's all the P stands for, is the left-hand side of the arrow, is true. If I know that, then I know that the right-hand side of the arrow is true. So I need 2 pieces of information, and it doesn't matter what order they're in, and I can deduce that the right-hand side of the arrow is true. It can look like this. A or B implies C and D. A or B, therefore C and D. And I don't really need the parentheses here, but I can put them around it. If A or B is true, then C and D is true. And if I know that the left-hand side is true, then I know that the right-hand side is true. Not J implies not K, not J, so not K. The left-hand side needs to be affirmed, and the way I affirm the left-hand side of the arrow is to have not J. I then affirm the right-hand side of the arrow, which is not K, and that's what I get for my conclusion here. It has to be an affirmation of the left-hand side giving me the right-hand side. There's a common mistake, in fact, it's even got a formal name in logic called the fallacy of affirming the consequent. You'll never need to know this, by the way. Which goes like this: P arrow Q, Q, P. That's wrong. Why is that wrong? Because I am affirming the right-hand side, not the left-hand side. To show you how this goes wrong, remember something we had from chapter 6. If rain, then clouds. If it's raining out, then it's got to be cloudy. And then I affirm the right-hand side. There are clouds. If there are clouds out, does it have to be raining? Well, not necessarily. It could just be a cloudy, overcast day. Or it could be snowing, or it could be sleeting. But there is no necessity that I have any conclusion at all that follows. So I have to affirm the left-hand side to do a modus ponens. Similar to modus ponens is the next little goodie, which is modus tollens. Sorry, we're not done yet. The last little goodie is modus tollens, and this is the method of disproving. I once again start off with an arrow, and this is MT modus tollens. I deny the right-hand side of the arrow, and therefore I deny the left-hand side of the arrow. I deny the right, so I can deny the left. So, if rain, then clouds. No clouds, therefore no rain. If rain, then clouds, no clouds, therefore no rain. I can't do it the other way around. I can't say, if rain, then clouds, no rain. Well, it might still be cloudy out, who knows? I deny the right-hand side, and so I can deny the left-hand side. Now, it's good to get really comfortable and do the same exercises over and over again, particularly modus ponens and modus tollens, because you're going to use those guys a lot as you're working problems out. MP and MT, so spend some time reading over the descriptions. I give you examples of correct use in the book, and I also give you a lot of examples of incorrect use, just to make you sensitive to what's going on. The next one looks very different from the others. It's called a chain argument. P arrow Q, Q arrow R, P arrow R. CA, chain argument. What this says, if I have an arrow and another arrow, and it has to be arrows, it can't be ands or ors, I can click them together. Notice that there is a common middle term here, P arrow Q, Q arrow R. There's a term that's on the right here and the left here. I can click them together. The Q goes away when I telescope them together. The P stays on the left, the R stays on the right. Chain argument. Anytime you see a problem with lots of arrows in it, start looking for a chain argument or two, because it's pretty predictable that that's going to happen. And again, this could be more complicated. I could have A or B implies C and D, and then C and D implies E implies F. I can click together these middle terms, C and D, and come up with A or B implies E arrow F. So as long as I have that common middle term, I can click them together and the left stays on the left, the right stays on the right. An example that might be helpful to you, if Fred is taller than Steve and Steve is taller than Joe, you can conclude that Fred has to be taller than Joe. That's one of those occasions where what you've learned in mathematics class actually relates pretty strongly to what's here. The reason it works is logically very different from greater thans and less thans, but ultimately this intuition applies very nicely up here. So that's called a chain argument. Last one I'm going to give you before we work a few problems is the disjunctive argument. The disjunctive argument does not start off with an arrow, so when we need it as we start working problems, it's going to be pretty obvious. I've got an or statement, not an arrow. The last three have taken arrows. So I have an or statement. Something's on the left and something's on the right. I deny one side of this. P or Q, P is false, so Q is true. P or Q, Q is false, so P is true. This is kind of a process of elimination argument. So here's what I want you to think about. Let's say my car keys are either hidden in my left hand or my right hand. They're kind of bulky, so I won't try to do this. My car keys are either in my left hand or my right hand, and given what the word or means in logic, I could be sneaky and have car keys in both hands. That would be okay. It's an or statement. I open up my left hand and say, whoa, there's no car keys here. Now, if I'm not a compulsive liar, you know where the car keys are. They're over here. This is true. This is false. Likewise, if I say I got car keys in both hands and I show you that the right hand is empty, it's got to be in the left hand, except, of course, I'm not really doing this right now. So it's an or statement. If one side is false, the other side is true. If one side is false, the other side is true. That's the disjunctive argument. Now I'll show you a few of the arguments in the textbook that relate to this to give you an idea of what it looks like to do these problems. And again, what I try to do is to build it up through problem sets. It doesn't seem in the book like it's all that slow, but when you get to it, it's going to be built stepwise. So in the book, we're going to start with problem set 8.2. And 8.2 just gives you 4 rules, the ones we just gone over up to disjunctive argument. And then there's the problem set for 8.2. And then I add some more rules up to 7, and then I give you problems built on those. So you know when you're doing 8.2, the only exercises, the only rules that you're going to need for this exercise are the rules that you've already encountered as you've been doing this. That is to say, the first 4 rules. So you don't have a lot to keep track of yet. But let me assure you that if you're starting to run into trouble with this chapter, go back and hit the first 4 rules a lot, because you're going to use them repeatedly, and frankly, if you're only using 10 rules, knowing 4 of them will get you through a lot of problems. So problem 1 looks like this. A or C. Line 2, not B. Line 3, not C or B. Conclusion, A. A or C, not B, not C or B. Okay. This is not that tricky, but I know the first time you look at it, it looks bizarre and intimidating. What I'm trying to do is to prove A. A is sitting here in a disjunction in line 1. I'm given 3 chunks of information to use, to process, to go to here. There's a couple of ways to reason this out, but the one that I recommend for most of these is what I just call connect the dots. I know I need to prove that A is true. Here's A. So probably the last thing I do is going to involve line 1. A connects to the letter C. C is also here in line 1. I look for another place with C and I find it in line 3. In line 3 there's the letter B, and the letter B goes back to line 2. After that I've used up everything. What I do is I start at the end and I work back to the beginning. So this B, this line 2, or here lines 2 and 3, because everything we do right now needs 2 lines, this is going to be the essence of where I begin. I find my beginning by starting at the end and working backwards. This is a very useful skill set. So the end of the line is 2 and 3 with the letter B in them. So just look at 2 and 3 for the moment. B is false, and then either C is false or B is true. I have an or statement here, and there's only one rule of the 4 rules so far that has an or statement. That is disjunctive argument. And again, you'll have this sheet with you, so you don't have to memorize the rules, but you have to know what you're looking for. So disjunctive argument says what? I have an or statement. I know that one side of the or is false. Whatever is left over then has to be true. And while this might sound a little funny, what is true is the left-hand side, which is not C. Now I have to justify saying that not C is the case, that C is false. I justify that by saying that I've used lines 2 and 3 and the rule called disjunctive argument on them. And if I want to, I can put little tick marks through 2 and 3, but they don't really go away. So I started at my conclusion. I worked backwards to the beginning. The beginning was this letter B stuff in 2 and 3. So I knew 2 and 3 is where I'd start. Since it's an or statement, I had to use a disjunctive argument. I got nothing else to do on or statements. And reading the disjunctive argument rule, if I have an or, and I know that one side is false, the other side is true, and saying the left side is true means I just copy not C. 2 and 3, probably we're not going to come back to them, so now this looks a lot easier. A or C, C is false. Conclusion that I'm supposed to reach is A is true. So what do I have to work with? I have to work with lines 1 and 4. There's an or statement here, so the only thing I can do is a disjunctive argument. A or C is true, but C is false. That tells me that A has to be true. Since A has to be true, I'm done, because that's where I've been told to go. This is all done stepwise again at the back of the book. So you're going to want to look at that and get a sense as to how that all happens here for 4-2. And as I've said several times already, the best thing to do if you're feeling a little bit challenged is to do the problems, look at the answers, and then come back to them later and see if you can do them after you've already worked them once. Okay? Problem 2. Line 1, E implies G. Line 2, G implies H. Line 3, F implies E. Conclusion, F implies H. One of your big challenges when you do these problems is to see what's going on. And that really only comes through experience. I've got, though, an arrow, an arrow, an arrow here in my premises and an arrow here in the conclusion. That strongly suggests the rule that is all about arrows, chain argument, rule number 3 on your sheet. And I know from what I'm seeing here, you're not going to be able to see the sheet. Make sure you've got the book in front of you with the rules out. So, chain argument. Chain argument says I can telescope 2 lines together. I cannot take 3 lines together and crunch them all together with a chain argument. So if your conclusion was 1, 2, 3, chain argument gives me F arrow H, that's wrong. You have to do it in pairs. Lines 1 and 2, they'll give you a pair. E arrow G, G arrow H. There's a common middle term, which is G. So what I can do here is to go E arrow G, G arrow H. E stays on the left, H stays on the right. G vanishes. 1, 2, chain argument. And put little tick marks through there. Okay? Anything below the line that I have deduced, I can now use as if it were anything else. F arrow E, E arrow H. F to E, E to H, E goes away, F stays on the left, H stays on the right, and that's 3, 4 chain argument. And there you go, 3, 4 chain argument gives you F to H. So you have to do this in 2 steps. You can't do it with 3 because the rule only works on 2 lines. We could theoretically have a lot more rules. We could have a rule that says you can crush 3 lines together. That would ultimately turn out to make sense. But you're only learning 10 rules. And frankly, adding more rules will not make your life easier. So all we're going to do is make sure we've got this down. Let's do one more from this section. Again, the point to this is to show you how to make sense of what you're looking at in the textbook. You will need to spend some quality time with the book. Now, when I ask you quiz questions, multiple choice quiz questions, they tend to have you identifying rules or asking about the last step in a problem. When it asks you about the last step, you're going to have to work the problem and then determine what that is. In the final exam, you will not be doing last steps. You'll be doing the whole thing, which might involve 5 or 6 different steps, depends on what the problem is. So make sure that you're not just looking at what's on the online quiz, because there's a lot of ways to do these correctly. That last problem had a couple of different solutions, and so as long as you give me a correct answer, you're good. But I can't in the computer consider every possible outcome. Okay, let's do 3. This again is problem set 8-2. Line 1, not K. Line 2, I implies K. Line 3, J implies I. Conclusion is not J. Now, even though you only have 4 rules here, there are actually 2 good answers to this. One is to look at these arrows and these negations and realize that we're doing modus tollens. You're going to see that when you think backwards. J connects to I connects to K. K is the beginning of the solution. If I look at lines 1 and 2, I goes to K, but K is false. I'm saying I have an implication, and the right-hand side of the implication is false. That's a setup for a modus tollens. Look at the rules. Rule number 2. And that says that the left-hand side is false, not I. J implies I, but the right-hand thing is false, so the left-hand thing is false. 3, 4, modus tollens. Okay, that's one kind of a solution. But I can do the problem a different way. The other way is to look at lines 2 and 3 and say, hey, wait a minute, J goes to K, I goes to K. I know that's a little hard for you to read. I goes to K, J goes to I. I have a common middle term, so I can do a chain argument with that. I can get J goes to K, I'll write this a little bigger, by putting together lines 2 and 3 with a chain argument. J goes to K, K is false, so J is false, and that's 1, 4, modus tollens. Again, notice you do know where you're going with this, and that'll give you some hints when you perhaps make a mistake if you're getting something that says the opposite of that. Either one of these 2-step solutions I would accept without any difficulty. They're both good. They both get you where you need to go, and they use rules that are appropriate. And if you were to add extra steps for some reason to some of these problems, I wouldn't worry about that, and I don't take any points off for that. Let's add a few more rules here. Again, work the problems in the book, check them in the back. Make sure you can do them over and over again and get comfortable with them over a passage of several days. Again, if this is the night before the last day to take the final, which is the Friday before finals week, you're very unlikely to pick it up quickly enough to be able to do well on the test on this section. Hopefully you're starting a little sooner than that. Okay, there's 3 more rules I'm going to give you to finish out the logical implications. Rule number 5, we already went over. This is simplification. Anytime I see a conjunction in my premises, I can tear it apart. Notice this doesn't take 2 lines, it just takes 1 line. It says if I have an and statement, I can tear it apart and grab either the left-hand side as true or the right-hand side as true. It's done mostly for bookkeeping, just to smooth out what you're doing. And it doesn't tend to be that hard to spot when you need it. Rule 6, and by the way, again, only with an and. If I have an or an if then, I can't use this. Rule 6 is the opposite of that. It's conjunction, and it says if I know that P is Q true and Q is true, then Shazam, P and Q are both true. Okay. If they're both true, they're both true. And I'm just putting them on the same line together, held together with an and statement. That's it. Again, that only works with the and. You cannot do that with the or with the if-then. The last one is rule number 7, and this is a weirdo. There is no substitute for this rule when you need it in a problem. It's called addition. And really, from your short truth tables, you should be able to understand how addition works. Premise, P. Conclusion, P or Q. If I know that something is true, P just stands in the place of anything at all, then I can know that it or anything else in the universe is true. Now, how do I know that? Well, this statement, P or Q, just says part of this is true. So if all I need to say is part of this is true, then I can do that safely knowing that P is true. What's Q? Doesn't matter what Q is. Q could be anything. Anytime you see a letter emerging out of nowhere in the middle of a problem, it's somebody's pulled an addition on you. That's the only way to do this. So when you need this, it's not very common, but it's very distinctive. If something is true, then that or anything else is true. And remember, that's just a placeholder. It's the left side of the or. Q is just the right side of the or. And it doesn't have to be a Q. It could be a W or some insane thing in parentheses. That's addition. When you need it, it's very distinctive. Okay? All 7 of those logical implications only work in one direction. They have to go basically from top to bottom as you're doing your problems. But let's work a couple of the problems here that are in set 8.3. 8.3 is, again, stuff using rules 1 through 7. So, a lot of this you're going to find is just bookkeeping, by which I mean there's just a lot of stuff to process. A lot of steps are going to be needed. None of them individually are all that tricky. If I reason this one backwards, I know that I've got to get to S. S is my conclusion. S is on the right-hand side of an arrow. It's connected to P and R. P's up here, R's down here, and they connect to O and Q, which don't go anywhere. A basic rule when you're working your problems is that if you see an and statement, tear it apart. You can't tear it apart inside of parentheses because the implications don't work in parentheses. But for lines 4 and 5, I can tear out the O and the P. And what do I say? O is true. Why? O and P are both true. O is true, line 1, simplification. P is true, line 1, simplification. And then this bottom thing, Q and R. Q is true, and R is true. And if you want to do simplification 3, that's fine. It doesn't really matter. Okay? So what I've done is I've taken 1 and 3 and I've torn them apart. Now I have to think about what I need to solve the problem. S is true. I need P and R to both be true to make S true by modus ponens. A lot of what you're doing here is backwards reasoning. P and R, I need them to both be true. Well, here's P true and here's R true. They're both true. So P and R are both true, and I can use those to show that S is true. But I have to put them together because they're together inside of parentheses here. So I need to glue them. How do I glue P and R together? I find them in lines 5 and 7, and I glue them together with a rule called conjunction, rule number 8. If 2 things are true, then they're both true, which as a rule does not sound that exciting, and you're mostly doing it so it looks right. P and R are both true. Now, if P and R are both true, which they are, then S is true. S is true, and that's going to be lines 2 and 8, modus ponens. If you want to be efficient, you do not have to do steps 4 and 6 because you never really need O and Q. But I will take no points off for doing something that's not absolutely required. Let's look at problem 2. Again, I'm on set 8-3. So I have T arrow U, V arrow W, and then I have not U and not W. I'm writing those kind of big so you can see what I'm doing. My conclusion is not T and not V. Now, I told you before that anytime you see an AND statement that's not in parentheses, you can take it apart. Not U, not W, 3 simplification, 3 simplification. It never hurts anything to do that. Now let's think about the problem. I need T. Well, here's a T. It's a T and not a not T, but it's T. I need a V. Here's a V over here. T is connected to U, V is connected to W, here's a not U, and here's a not W. The T and the V are not together anywhere, so I'm going to have to fix that at the end. And when I said that online you're going to have questions about what's the last step, the last step, once I've got these two, is to click them together using what rule? It would be a rule called conjunction. Again, you'll have all the rules in front of you, you just have to use them correctly. Line 1, line 4. T implies U. U is false. So I have an arrow, and the right-hand side of the arrow is false. That means the left-hand side of the arrow is false. 1-4 modus tollens. I look at 2 and 5. V implies W, W is false. V is false. 2-5 modus tollens. Modus ponens and modus tollens you need to learn till you can work them inside and out. Conclusion, T is false and V is false. T is false, V is false, so I just glue them together. And that's going to be 6-7 conjunction. Again, don't be afraid to put these aside and then come back and just try to do this same problem. Because the stuff on the test, and there's going to be 6 problems of this sort, does not particularly go past anything you've seen. In fact, a lot of it is relatively simple if you've been watching this. So this is a fairly complicated one, and this makes use of simplification and conjunction. I'm going to do one more of these, and then we're going to take a little break and then look at the last few sets of rules. And again, I'm only going to give you the next 3 that come from the logical equivalences, but work some problems using a variety of sources. Let's do problem 4. So this is going to be 8-3, problem 4. And it looks like this. X or y implies z. A implies x. A, conclusion z. Reasoning this backwards, z is my conclusion. It connects to x and y. Y is nowhere else in the problem. X is here. X connects to A. A is where we start. So I look at lines 2 and 3, because that's where my A is. A, if A is true, then X is true. A is true, so I can look at 1, 2, and 3. At 2 and 3, A is true. If A is true, then X is true. I can deduce that X is true by modus ponens. And again, if you just sort of say all this out loud, it doesn't sound all that crazy. If A is true, then X is true. A is true, so X must be true. 2, 3 modus ponens. Now I have a puzzle. If X or Y is true, then Z, my destination, is true. Good. I've got X, I don't have Y, and in a sense in my head I can read this out loud and say, well, if X or Y is true, well, I know that X is true, so that's good. Then Z is going to be true, and there's my conclusion. But I need to match the format exactly. I need to pull Y out of the thin air, and there's only one way to pull something out of the thin air. That is the rule called addition, and addition only works on one line. Line 4, addition. I take that X and I do an or Y to it. Now in the rules, it's a Q that gets added to it. Doesn't matter. Anything can be added with an or connective. Once I have X or Y implies Z. Z is true, and that's going to be 1, 5 modus ponens. So it takes 3 steps to solve this one. You have to recognize the value of the modus ponens, and then you have to know that the addition is needed to clean all this up and to finish it off. Okay, so we're going to take a pause at this point, and I'm going to introduce the last 3 rules to you, and we'll work a number of problems, some of them from earlier in the rules, some of them from later. Mostly these are going to be coming out of the little review section at the end of the chapter.